Hello, for today's video, I had an interesting idea. I was thinking of taking an RGB LED, which if you can see here, it's just an LED that has three terminals, red, green, blue, and either ground or anode or cathode. It doesn't really matter. But I was thinking of taking one of these and feeding, instead of just a high or low voltage on the LED portion, just give it a sine wave and give each of the leads a unique sine wave. Especially if I slow it down, we might get this interesting effect of all the different colors going shifting through it. So I thought that would be kind of cool to look at. So that's what I'm going to do. Alright, so in order to generate those sine waves, I decided I don't want to use a microcontroller. I think it'd be fun to do this all analog. And there's a circuit you can do to do just that, to make a sine wave. It's called the Wien Bridge circuit. Okay, so this is the circuit, and to give you a quick understanding of how it works, it uses positive feedback, so this output feeds back to one of its inputs, and the output is put through a bandpass filter, which basically only allows a certain group of frequencies to go through. It's pretty narrow in this case. So with positive feedback, noise on this line triggers the output to start outputting, and then as it goes through, most frequencies are attenuated to nothing, while the ones that this is designed for actually exists. So in this circuit, if you have the resistors and the capacitors as the same value, then the frequency you actually see that starts to rise in the output is given by 1 over 2 pi frequency, 2 pi RC. So that's the frequency that gets generated by the circuit. An important note is up here, you have the amplifier portion of it. So in this case, 2R over R is a good choice because the gain of this configuration is 1 plus R2 over R1. And this bandpass filter, I'm not going to go over the derivation of it, but for this frequency that pops up, it actually gets attenuated by about 1/3. So whatever's here, V out, gets attenuated by 1/3 when it gets to this point and feeds back. So if you want the positive feedback to work, you need to counteract this 1/3 with 1/3 of your own, or with a third, with a 3, which is why 2R versus R gives you gain of 3, so it balances out. Another important note is the point here. This is a reference to ground, and this is a reference to ground. But if you want this to work, you can't have the op-amp powered with ground. You have to have it powered with negative VCC. So either you can have a dual output power supply, or you can, instead of making this directly to ground, you can give it a midpoint reference, so like half of VCC. And then we can, instead of negative VCC, we can just have this connected to ground. And this will also work. So the thing with this is, in practical creation, it doesn't always work out if you pick the right resistor values. First, the resistor values themselves vary a little bit, just for manufacturing, and also voltages. It's kind of you switch it out until it kind of works. And I'm going to show that now. So, to an actual circuit. To just give a quick heads up of what I'm going to do. These are 3 op amps, so I'm going to set up the circuit on the circuit I showed on the whiteboard on the bottom portion of these, and on the upper portion, these have 2 op amps in them. I'm going to set up that reference circuit. And I think I might do a custom one each, or I might have just one of these generate the reference for all of them. The thing is if you can have multiple references, you have more chances to customize it, but for simplicity's sake, I might just leave one reference maybe in the middle. So I'm going to build that now. So here's the circuit. I went ahead and made all 3 sine waves. I still need to go over these values to confirm everything is working, but I built it so it's kind of customizable. So right now all of them use one voltage reference, but it's wired so that it would be pretty easy for me to insert different voltage references. I also tried to make this, in my previous times I've made this circuit, it was too hard to replace components, so I gave them enough space that it would be a bit easier, and you know, there's 3. These are all the outputs, so I'm going to verify the values on these and then see what each of them are outputting. Alright, so we can see right here the system is powering 3 LEDs. We'll go through the first one, which starts at the left. So on the oscilloscope, this is the output of this oscilloscope probe here. And we can see it is close to a sine wave with some clippage at oscillating about 350 hertz, if that will pop up. 320 hertz, somewhere around there. So we can see that, and that's faster than we can see with our eyes, so that's why it looks like it's almost solid. If we go to the next one, we can see here it looks a lot less visible. So let's see. So this one looks like it's not actually outputting that much of a sine wave. In fact, it just seems to average around 2.4 volts, which means that this isn't really oscillating right now. The reason the LED is still on is because the high side of the LED is always powered, and since this is 2.1, it's just providing some current. So I'll have to see if I can fix that. And for the last one, we have it clearly oscillating, so if we switch the probe to the low side, we can see it's on a much more recognizable scale. So we have to really bring it back, and this thing takes a while once it's sampling at about a second. I'm going to give it some time. Okay, we can see here it's more just oscillating, not really a sine wave, but at least it's going up and down, and we can fix this by reducing the gain on the output, because right now it's just amplifying way too much, so it reaches its bounds for the entire time. In fact, I assume that the second LED has the opposite problem. I'm going to double check the circuit, but I think it may just not have enough gain, so it doesn't actually build up that positive feedback. So I'm going to see if I can get both of these to look a little more smooth. Okay, so back at it. I think I fixed it. So all I did here was originally I had 20K on the lower part of the amplifier and I believe 47K on the upper. And that was, you know, about 2.5x. So instead I replace it with 100K and 220K, which is much closer to 2 times. Honestly, I'm just using what I have on hand. So, but we can see here I'm looking at the middle waveform, and that was the one that was doing nothing. On this one too, originally actually the capacitors were only 56 picofarads. So I jumped those up to 100 nanofarads, and now we have frequency of about 80 hertz, something like that, and it looks pretty good. With the change of amplifier, I'm going to switch it back down to this lower waveform, and oh, looks a little weird. Oh, actually, I have that plugged into the wrong section. That's not actually the output waveform. Okay. Yeah, so we can see here it's a bit closer to an actual sine wave. A lot smoother, but I could do to probably bring the gain down on here as well. But yeah, so that's the fixes, and now I need to decide what I'm going to do next. Okay, so all the sine waves are there that we need. So all that's kind of left is to plug in a RGB LED and tune the system to see if we can make it make some interesting lighting. One thing I might also do is, right now the sine waves are directly feeding into the LED, and I might put a buffer stage using some more op amps to see if that smooths it out or something like that. So I'm going to set that up now and we can start seeing like what does it look like on a natural RGB. Okay, here it is. The outputs are staged with these buffers, feeds into the RGB, and this is a knob to adjust the brightness. So I'm going to turn on the power supply and adjust, I said that pretty weird, adjust the LED to turn on. So it actually takes a second because of the sine wave needs to kind of kick in, or I just didn't turn it on fast enough. So yeah, we can already start to see this is starting to look pretty interesting. The frame rate of the camera might be not making it appear as smooth. Or maybe just the frequency I have is a little too close to the shutter speed. So, but as you can see here, like if I adjust it, we can start seeing the sine waves or some of the effects pop up. So what I want to do next is start adjusting the actual frequency of the sine waves behind it and seeing if we can get a bit more of an interesting effect. So this is what happened when I switched out 47 picofarads for 33 microfarads. We see that don't know which color it is, but that one is like flashing a lot more now. I mean, again, I can adjust the frequency or adjust the brightness here for all of the LEDs. I'm going to mess with the middle circuit because I think its shutter speed is it's too close to the camera shutter speed, but maybe see what happens next. Alright, here's another one. I decreased the frequency of the one that was flashing a bit quickly on the left by just increasing the two resistor sizes here. If you remember, the frequency is governed by 1 over RC basically, and so now we're starting to see, with this slowed down effect, we can start seeing different patterns emerge as they oscillate in and out of frequency. We can see like the different effects, which is really cool. What I want to try is if there's a way for me to either adjust the frequency a little more easily, because I have to pull out the parts here and switch them out. I have an idea, which would just be taking a capacitor and placing it maybe in between the connection and see, what that does. I think that would delay it a little bit, maybe do something interesting, so I might try that next. Okay, so let me bring this down. There's a few interesting things I can do to adjust the lighting of this. So you can see right here, it's doing this effect, but let me get down here. I have a capacitor right here, and what I could do is take this capacitor and apply it in parallel with one of these resistors. So the easiest way I think to do that would be maybe I can take right here. I'm going to target the leftmost lead. So if I place this here, and then I take, let's say, I think this will be easy. So I'm going to put a wire down here and connect it to this male to female so I can probe a little easier. And now I have this capacitor tied to the line, and I'm going to connect it just to, let's say, to the other line. So we can see now you have these pulses of green that are interesting, and it's starting to like create this new pattern. If I release it, we should see it return to a similar state as earlier, if not just a new state. I'm not actually sure what would happen. Now if I try this with maybe, instead of the far most right lead, I could try this with the second from the left. I think this is still connected. Yeah? Okay. So we can see now it's starting to shift its color again. If I do this with maybe this lead, It also would probably change the effect if I do it from the other side. So this is pretty interesting. Like, just once we set up this system, we can start, having fun with it. Maybe shifting a couple more things. Another interesting idea could be to take, this is a capacitor that's pretty big for a ceramic, but maybe I could take this very small one, might not even have an effect, but I could place this, like, let's just say even, we'll put it parallel between the two leads over here. I can't tell, it's hard to tell what's actually making a difference anymore. I can't really notice. But no, yeah, so we can start seeing, this is exactly kind of what I was going for, an interesting effect. And I feel like there's a lot of ways that you can change this system in order to get more interesting effects. For example, you could put, you could probably smooth out the sine waves. You can continue to change the frequency. You could maybe figure out how to make these more out of phase, make it a little more controllable. That was interesting. See, all of those at the same time just now were all flashing, going off and on. And that's actually, right now this is interesting, because I think the system maybe balanced itself out, but if I try to reapply the capacitor to the system, we see this like more solid effect where red is on for a longer time, green is on for a longer time. And it's probably because if one's high, the other... Well, honestly, I don't know. Just shorting things, I don't actually have a conclusion. But instead of targeting the LED lead, I'm actually going to take it to the output of some of the other signals and see what happens. I actually quite like this one. So it's if I just fully plug it in, it kind of has this nice like flash of orange and blue. So I figured it's also interesting to show you guys how the oscillation builds up initially. So I'm actually going to turn it off and just show you the oscilloscope of a signal starting to build up. So the moment I turn it on, we'll start seeing on here, it starts off slow, but the oscillations actually grow over time. And that's just the positive feedback of it. Until eventually it reaches this maximum. And I believe actually this clipping, part of the problem with the clipping is if you have a slow frequency, it's going to charge up, or it's going to spend more time trying to amplify it, which leads your waveform to have more time to get to the rails. So, I mean, I guess my theory of if you wanted to actually fix that would be you would need some kind of output capacitor to slow down this this rate of change. And in fact, because this is going to be rail to rail, what I'll actually do is see what happens if I take maybe like a 100 microfarad and just buffer the output of the signal with that. So we actually buffered the input stage, and it doesn't actually appear to be doing anything. Okay, so I switched it out for a much bigger capacitor, and we can actually spot a difference in the waveform now when I have the capacitor in versus out. So you can see here, this is with it in, and if I were to remove it, we can see actually that the bottom side gets a bit more clipping, and the top side gets a bit more clipping. And it's also interesting that the discharge of it is a bit smoother, while the charge up is about the same. But yeah, I'm going to leave that at that. So yeah, this is quite cool. I think this is awesome. So I think I might leave the video off there, and if I turn up the brightness too, we can see some more effect. Yeah, so let me know if you're interested in me fooling around with this more. I'll hold on to this circuit. I won't get rid of it. Yeah, so just let me know. See ya!